the reality is that you never have a spring that's complete acting purely in compression, in static compression. Most of our springs, the way they work is they actually are subject to some fluctuating loads. Think about a car. You got a shock absorber, and you're riding the car, you hit a bump, and it goes up and down, and it stops, and it hits another bump and goes up and down, and it stops. So that spring is constantly going up, is compressing and uncompressing, compressing, uncompressing, and that's going to have a life cycle that's going to tend to create high fatigue concentrations around the coils that with time they wear out and they break. Okay, and not talk about there may be some small flaws or imperfections in your structure. So that is the motivation. So that is the motivation for this next topic. We will talk about the fatigue of helical compressive springs. So to start this discussion, the first thing you always have to do is you have to do your static analysis. You cannot start any, not even the spring or any substructure, nothing. You always do your static first, and then you check for cyclic loading. Okay. And so as the first check we want to do in the problem is we need to do your SN diagram. Okay, and to do your SN diagram, we're going to have to we're going to need to find your FS, and this FS is typically given at these life cycles that you have here. You can see that 10 to the 5, 10 to the 6, 10 to the 7. This chart is not in your textbook, and there should be a comma there, and depending on the different treatments is if it's pinned or unpinned. These are treatments that are given to the spring that actually adds life to the spring. It's a treatment against rust and other surface treatments are given there. Okay, so when you're talking about pinned, you're talking mainly. You can see that your FS will be higher, right? And if it's unpinned, you can see these values will be lower. These are percentages, okay? So if I say this is like 36%, okay, of the ultimate, but we write 0.36, and that's the number that will go there, and you have three different values for three different loads. Okay, but we will get to that in a minute. So most of the problems we want to do is we want to design them for infinite life. The springs are designed typically, I mean, rare case, they're not designed for infinite life. So to design infinite life, typically you have the amount of years you want the spring to last. Because remember, infinite life is not like you will use it from generation to generation to generation. It is that will exceed the life of the structure in which it's going to be applied to. As for an example, a mechanical pencil, um, if you consider the mechanical pencil, the life of a mechanical pencil is maybe a couple of months, 6 months, or maybe for a year. So you want that spring to last you at least a year and a half, if you would. And if you're talking about a shock absorber car and they give you a lifetime warranty, well, the lifetime warranty really means that the life of a car is going to be about 20 years, right? So you know that shock is not going to last you 20 years. So probably after 10 years, 6, 7 years, you're going to change the shocks of your cars anyways. So you want those springs to actually outlast the 6, 7 years. So maybe design them for 8, 9. So that's what we mean by infinite life here. So in this case, if we have number of years, 1 year, 52 weeks, 1 week, 48 hours, 1 hour, 60 minutes. And these are basically the RPM given in the problem itself. So if you think about the spring, right, and your spring, um, your spring is preloaded at some point, right? If this is your spring, it gets preloaded, and then from the position of preload, you're going to apply some cyclic loading, and that cyclic loading is going to have some frequency, okay? And that's and your load is experiencing that frequency. It is being excited at a omega. okay? And then typically, if these life cycles are 10 to the 7 and above, this is for infinite life. You're going to see that most of the applications, that's the way it is done. Okay, so the next thing we want to do is, if you remember for your static analysis, we have to calculate this guy. This is your ultimate tensile strength. And the ultimate tensile strength comes from the next table. And you can see from here that we calculate your exponent m and your constant a. And so as we spoke last time, this is another way you can write these, and depending on the material property that you're working with is the application, is the number that you will choose, right? This is just a handful of data. There are many more handouts out there with a lot more explanation, and this is your table 10.4 of your textbook. So then we go ahead and once we have this, we calculated this, then we're going to go ahead and we're going to find your ultimate shear. I don't know if you remember when we were discussing the analysis of I gave you introduction fatigue. I told you that in many cases what we want to do is we want to design this only for shear, right? Pure shear. If that was the case, then your fatigue diagram will look something like this, and respect to n. So it's pure shear. So here you don't put ultimate, you put ultimate S, okay? And that's going to come all the way down here probably. And this is going to be your endurance S, okay? So your fatigue diagram is going to look something like this probably, your life diagram. Um, and we will talk about what this diagram actually is going to look like. It is going to be a little bit different for these materials because then we have to, actually it's going to be Fs, and this is defined at infinite life after 10 to the 7. But we will get to that in a sec. So in the next chart, if we go to the next chart, you will see that these are, and this is, by the way, there is a handout that's posted online that you can follow. Basically, it has all this information. You can see that what happens here, this is a 10 to the 3. At 10 to the 3, you have to calculate the Fs, okay? And that Fs, I'm going to tell you in a minute how that's calculated. But then think this is actually going all the way up here, right? At some point you have 10 to the 0. And that 10 to the 0, that is the location of S ultimate S shear, okay? So, and then these values that you have here, these values that you find here, these values come from this table right here, right? This value 10 to the 6, 10 to the 7, 10 to the 9. You can evaluate this, you get different values. And those are the values that you basically are going to be expressing in this table. And anything beyond this point, this will actually give you an infinite life. And this is just a model for 228 music wire. Yes, this table is not in your textbook, but I'm giving this as a complementary information. And then at 10 to the 10 to the 3 cycles, this location right here, we will find that by basically multiplying 0.9 times SUS, or you can approximate that, just multiply 0.6 times the ultimate tensile strength. So then you have 10 to the 6, 10 to the 7, 10 to the 5, 6, and 7. And those are the numbers you place in here. And that will give you these values that you need so you can plot this diagram, okay? So now let's proceed. And note that the one thing I need to know is what is my endurance limit, okay? So now the endurance limits, when I calculate my endurance limit, there are two methods to do this. This is the first method, and I prefer this method. It's not in your textbook, but it's widely used. And it's actually a conservative method. This is all based on heavily on experimental data, and many times we just don't have all the data available. Okay, so So basically, it consists in if it's unpinned or pinned. So you just choose depending on the application that you have in your of your spring. And this is K infinite. And note that your K infinite is just like if it's a room temperature, it's no corrosion, 50% reliability, then this is actually equal to 1. This is just like before, we need to correct your value. So if it was not a room temperature, then yes, you have to make a correction for T. Just as we did before, if we another reliability factors there, we need to take that in consideration. If there's corrosion, then you add that. And you say anything else that you may have to add to the spring, you can do this. But that will depending on the spring application. Okay, so here in this course, we will just stick with k equal to 1, and we're going to make this assumption and move on with that. So with this information, knowing that I have this value, I have this value, right? Where this comes from here. And so I can find what my endurance limit will be. Okay. The second approach, this is what your book recommends. It's kind of a same approach. Is unpinned and pinned. So you're going to choose one of those values, and the same thing for room temperature. Use k equal to 1, and if it's not 1, then you make your appropriate corrections. As I did in the previous chart, just remember this is equal to kr, kt, and maybe ke or anything else that you have to add there. And given these values now, you're going to find your endurance limit. Please note that these values come from here and this value comes from here. This is not from your actual load, okay? Not from actual load, okay? This comes from this data, okay? It's all related here, okay? From here, then you can calculate this value. So this is just material-based information. Okay, so then given this, and you wanted to find the life cycles in any other location, you got 3 points. Typically, you'll just do a straight line, so you just need those 3 points to evaluate this. And if you wanted to have what happens at what's the life cycle at any point here, you can always draw an answer diagram. Find the A and B. Remember, you have A and B on this segment, A and B on this segment. As you can see, they're straight lines. And one thing that's very interesting is that for springs, this is heavily dependent on the value of D. Okay, and like in other examples, maybe it was not depending on D. Here it is, because your ultimate value is actually depending on D, right? If you change your D, this is going to change. Okay, so so that's important. The next thing we want to do in the problem is every time we start, we want to apply a design factor endpoint, a design factor 1.2. Remember, this is just a standard. The problem doesn't have to tell you that. For springs, it's 1.2. In many cases, that's going to be one of the examples we will do. We want to add an additional factor 1.2 or 1.5. If that was the case, then your design will be new design factor will be 1.2 times 1.5. So you see that we need to modify your the preload. You need to modify your maximum load, your minimum load, in which this is actually fluctuating. And don't forget to always do your strength and stability checks from your static analysis. All those checks needs to be first thing that we do in the problem. And typically what we'll use is we'll use your preload and we'll use F maximum for this analysis. Okay, so you use your F max, you will evaluate this as Fi, and also evaluate this as F shut. And the other thing that you have to check, you have to check for stability to make sure this is less than L critical. Okay, so those are the things that you have to keep in mind and all the problems that has to be done. So as we move on, what we will have is you calculate your maximum and minimum that are given in the problem. They are not you got some preload, so you're going to be in compression. From that preload, then you're going to have some location where you're going to be fluctuating, right? In this problem, this will be your F max, and this will be your F minimum here at the bottom. Okay, so this is where this is bound by. Okay, and this is actually acting over a delta delta clearance. Given those values, then we can find your alternate and mean forces, and from there you find your alternate and mean stresses. Um, and with that information, given that information, then we can go ahead and we can calculate your fatigue stress. Your fatigue stress, this is how we're going to define it. We keep it like this. It looks like redundant, but that's in case you have to apply sometime another factor or something there. At this stage, you could do that. When we do fatigue analysis, we want to always find the S max. S max is the mean plus the alternate. And we always want to make sure that S max is always less than your yield strength. That's the static check in addition to the static analysis. Okay, this is different. So then to understand your fatigue strength or Goodman theory, what you have to know is to keep in mind that we have here, we didn't have before, is we have a preload stress. Okay, and this is your Goodman stress. This is the Goodman line that we're going to do. And this is your failure point. This is your load line. And note that your load line now is not going to be equal to tau A or tau M. You have to subtract this tau I. Why? Because now in this problem, you're going to have a preload. Before we were starting at 0, so this was one-to-one relationship. Now we have shifted, and we had to consider that into the equation. Okay, so once we understand this, so this is what we are really trying to do in the problem. So now we move on and we calculate your maximum mean stresses. This is, again, these are different variations, right? You can use any variation of this equation. This is same from static. Remember, you have to calculate this at your preload as well. We're going to need the stress, so we can determine the load line, as I just told you previously. Your Goodman equivalent stress for torsion, for springs, sorry, is given by this, where all these values, this here is from your actual loading. This is your actual loading. Those are the values that you're actually getting from here. You're getting from your actual loads. These are, you missed this one. This is your loads. Okay. This is where this is going to come from. And if it's, you always want to make sure this is less or equal than SC, so it's infinite life. It's bigger than its finite life. And you can actually check how much life you have left by using your SN diagram. There's one more check that you can do for this type of analysis, and that is you can check for your strength, and your strength is equivalent by divided by SA, and that has to be bigger or equal than 1. So there's another approach. I just want to mention it. It is in your notes. You can also use, instead of Goodman, Gerber theory, which gives a very good analysis using your test data. So this is the same as before if I was going to use your textbook, or you can use use your textbook values from 1028, 1029, and then make the corrections as we already discussed. And just know that the difference is now you have this squared. Since this is squared, then these equations actually become completely different. And you can see how your preload is going to affect your R, and that's where your R is inside here. Okay, this is another way you could calculate this, and this has to be less than sigma SE. Okay. Uh, this one last check that you have to do for springs that you didn't have to do before, and is you need to check the frequency. So to the frequencies, this is the weight. Remember, the weight is m times mass, and this is the same times um, rho times volume times g. So rho times g times volume, and this is nothing else than gamma times volume. So this whole thing is the volume. This is the volume for spring, and then this is your specific weight of the coil. And this is already given in data. You have the information from tables. And what you want to do is you want to calculate what your natural frequency is, and that natural frequency, your real acting frequency has to be less than that. So how you calculate in RPM, this is actually given in RPM. So this is a very convenient way of using it because that's what typically we have. And you can see in one case, this is if both ends are in contact with plates, only one end is in contact with plate. So in case you have a spring like this and this is attached, another case you could have, and this is a load applied right there, but it's slide free. In this case, you got the spring attached like this, and you're applying the load to another plate. Okay, if they're both ends are they're in contact with plates, like in this case, then you use this equation. Otherwise, you use the other one. It's very difference is 1/2. And to avoid frequency resonance, you want to make sure this is satisfies this criteria. This is the operating RPM. RPM. And what happens is, yeah, this is 15 and 20. Yeah, sometimes we can go as small as 13, or we could go as high as maybe 21 or 22. Typically, we like to stay within 15. So we're going to design in this particular course, we're going to make sure that you stick within 15 criteria. And then remember, every spring, there's no way to fit one spring into every possible design. So this concludes the basics of the theory for helical compressive springs.